Hello everyone, let's wait for 5 more minutes, then we can start the lesson. Hello everyone. Can someone confirm if I am audible and the screen is visible? Please type it on the chat box if I am audible. Okay. Yeah, so I think we can start our session. So, yeah, thanks. So in the previous week, we covered, we had the live session on basics of number system. We also saw a few examples related to performing conversion from one number system to another, like decimal to binary and hexadecimal. And we also performed a few operations like addition of hexadecimal numbers and other things. So in today's session, what we are going to do is we are going to focus on floating point numbers and introductory Boolean algebra. So my name is Arpit Bal. I am a PhD scholar at Department of Electrical Engineering at IIT Bombay. And so let's start the course. So first let me introduce a few basic things that we need to do before jumping to the problem. So the first thing that we need to know, so the first thing that we need to know is floating point number. Okay, so basically floating point representation is it refers to the particular representation in which there is no fixed number of digits before and after the decimal point. In simple words, it's a way of representing a number with the fractional part in computing. Okay, and we can represent that floating point, represent a floating point number in various forms. So IEEE has specified a particular standard, like we have single precision floating point and double precision floating point. So while representing a floating point, what we need to represent is the first bit is usually the sign of the floating point. So if it is equals to 1, so it means the number that we are trying to represent is negative. If it is equals 0, then the number that we are trying to represent is positive. Then we have a field called as exponent. So exponent basically indicates the power of 2. Indicates the power of 2 by which the significand is multiplied. Okay. So the next field is the significand. Okay, let me write down what is exponent. So exponent, it refers to the power of 2 by which significant is multiplied. Okay, and what is significant? So significant, it refers to the fractional part of that floating point number. Okay, so IEEE, it defines two standards. One is single precision floating point and another one is double precision floating point. So in the single precision floating point, what is defined is the number of bits that can be used for the exponent field and number of bits for the significant field. So in single precision floating point, we have 8 bits exponent and 23 bit significant, okay, along with the bias of 127. Okay, so what is a bias? It is basically something that needs to be subtracted from the value in the exponent field to determine its true value. Okay, similarly for the double precision part, it uses 8-bit exponent, it uses 11-bit exponent and 52-bit significant. Okay, and here the bias is 1023. Okay, so this is just the basic, and we can start with the numericals. Okay, so the first question is, we have to find the single precision floating point binary equivalent number of 23. Okay, so here first what we will do is we will convert 23 into binary form. So just like the previous examples that we did in the week 1, what we need to do is we need to divide it by 2. Okay, so if we divide it once, then we get okay, so the representation is something 10111. Okay, that is the decimal representation. But according to the IEEE standard, what we need to do is we need to represent it in a form like there should be a 1 that will be implied and then the rest of the digits. So if we want to represent this in this format, we will have 1.0111. So yeah, sure, Animesh. Okay, after this question I will take that out. Okay, so 1.0111. So earlier the decimal point was here, so we have shifted it to the left by a position of 4, right? So it will be into 2 power 4. Okay, so in the IEEE floating point representation, that the single precision floating point representation, what we do is in the significant field we just write the portion excluding the implied one. So it means if in the significant field we write 0, 1, 1, 1, so it will mean that we are going to represent 1.0111. So 1 is already implied. Okay, so and the exponent here mentioned is 4. So let's write it down first. Exponent is equal to 4. What is the biased exponent? Okay, so the bias exponent is 4 plus 127, or we can write it like this: 0 1 0 0, and just append the number of zeros before this thing, and we have 0 1 2 3 4 5 6 7. Okay, and it will be 1 3 1 1. So this is our exponent, sorry, this is our biased exponent in 8 bits representation. Okay, and the significand is 0 1 1 1, and rest you can append the number of zeros so as to satisfy this particular thing, that the number of bits that should be present in the significand is for the single precision floating point representation by IEEE, it was 23 bits, right? So what you need to do is you need to append, so we have already 4 bits, so we need to append 23 minus 4, that is 19 zeros. Okay, you just append 19 zeros. So, and this number is positive, so the sign bit is 0. Next is the exponent, so the exponent is 1, 5 zeros, 1 1, and the significand, so the significand is 0 1 1 and then 19 zeros. Okay, so let's see which option matches this thing, that is option A. Okay, yeah, so Animesh had a question, so Animesh, please go ahead. Sorry Animesh, like I can't unmute the mic, but if you have a question you can type it in the chat box. Okay, anyways, let's move to the next question. Animesh, meanwhile you can type the question whatever you have. Uh, yeah, Devadrita, I can repeat this point. So, okay, so you understood how we converted 23 into into binary, right? 10111. Okay, so what we need to do is, so this is a particular representation of the decimal in binary, but what we need to do is we need to represent in the IEEE single precision floating point format. So in that IEEE standard format for single precision floating point, what needs to be done is you need to represent that binary number in a format like 1.xyz into 2 to the power n, where n is the exponent and 1 point something is the value that you want to represent. Okay, so as we see that after converting into binary we have 10111. If we want to convert this thing into something like 1.xyz, so it means we have to move to the left of this decimal point by 1 2 3 4, by 4 locations, right? So if we are moving to the left by 4 location, it means 1 point something needs to be multiplied by an exponent of 2 to the power 4. Is that point clear? Okay, so it means the exponent value is 4, and as it was mentioned earlier that it needs to have a bias of 127. So what I did is I added 4 plus 127 to get the biased exponent, because in that particular field, in this particular field, that sign, exponent and significand, okay, so this exponent actually represents the biased exponent. So what we need to do is we need to add 127 to it to make it in the biased exponent form. Okay, so is this point clear? Okay, So the next thing that we did is, so the next field that is left with us is the significant. So for representing the significant, so what is biased exponent? Okay, so biased exponent means that you add the bias value that has been given by IEEE. So usually the bias value is something halfway middle the full scale value that can be presented. So in this particular case, what we are doing is we have an exponent field which is of 8-bit wide. So 8-bit wide means 2 to the power 8 can be the maximum value. So 2 to the power 8 represents 256, and halfway 256 is 128, and so that's why 127 was associated as the bias value by IEEE. Okay. So bias value is basically something that needs to be subtracted from the value that is present in that exponent field, the final value, so that you can determine the true value. So currently we are moving from true value to biased value, so we need to add 127. Okay, I hope that part is clear. Then in the significant field, what we do is we ignore the first one that is present just before the decimal, and we write whatever is present after the decimal in that significant field. Okay, so I hope that question is clear. Then then there is another question. In 14-bit floating point representation, why the value is 16, not 5, not 15? No, it depends whatever bias value you can take. So if you define the bias in that way, you can have 16. Means here also what we can do is we can assume something to be like instead of 128 I can say that it is, sorry, instead of 127 I can make it 128. But this is the standard that has been defined by IEEE, so we have to follow that. Does that answer your question, Animesh? Okay, where do you still have the doubt? Okay, then we'll come back to your question at the end. Okay, moving on to question number 4. So moving on to question number 2. Yeah. So moving on to question number 2, what we are given is we have a value minus 0.75 in decimal, and we need to represent it in the IEEE single precision binary format. So as it was discussed before, that the IEEE single precision floating point format, so the first bit is the sign bit, next is the exponent, next is the significant. Okay, and in this case we can see the number has a minus sign. So if the number has a minus sign, then what we will do is we will set the bit as 1, the first bit that represents the sign of the whatever number is present. Okay. Then next what we need to do is we need to convert 0.75 into binary. Okay, so 0.75 means we can say that it is 0.5 plus 0.25. Okay, yeah, here you can either go by the multiplication method, that you multiply it with 2 and find out what are the bits, but in this case it is pretty clearly visible that it is 0.5 plus 0.25. So 0.5 is in binary is 0.1, that is 2 to the power minus 1, and 0.25 in binary is 0.01 or 2 to the power minus 2. Okay, so 0.75 is basically 0.11. Okay, so if we want to represent it in the IEEE standard format, then we need to have something like 1.xyz, as it was mentioned in the previous, as it was done in the previous problem. So here also we need to move the decimal point to the right. So we will have 1.1 into 2 power minus 1. Okay. So here the exponent is minus 1. Let's write it down. Exponent is equal to minus 1. And to get the biased exponent from the exponent, what we need to do is we need to add 127 to it. So 127 minus 1 is 126. Okay. And now what we need to do is we need to just represent 126 in binary. So it is 0, 1, 1, 1. 1, 1, 1, 0. Right? So we have the exponent and we also have the significand. So the significand is only 1. Okay. So let's write down the exponent. Okay, there's a question. I said convert 0.75. Yeah, so Devadirita, yeah, that's true. So whenever you have something after the decimal point, we follow the multiplication method. So it was described in the previous live session that we had. So you can go through that again. And anything which is before the decimal point, whatever value, let's say we have something like 5. So 5 needs to be arrived at the binary value by using the long division method. So anything before the decimal point, long division. Anything after the decimal point has to go through multiplication method. I hope that answers your question. Okay, so let's write down the exponent field 0, 1, 1, 1, 1, 1, 0. Okay, so we have the exponent. Then what we need to do is find out the significand. So the significand is only 1, and the rest, whatever 22 bits we will have, we will append zeros to it. Okay, so now let's find out what is the correct solution. It is 1, 0, 1, 1, 1, 1, 1, 0. Yeah, so the correct option is A. Okay, so we have one more question. What is the industrial application for this representation, or simply why should we know about these representations? Okay, so I can tell you about one application, one such application. Let's say you are a DSP engineer and you have to represent, you have to make a filter. So usually what happens is the filters have coefficients like 0.1117 or 0.232, 0.16 something. Okay, but the usual way in which we represent binary numbers, it is something like 1 1 1 0 1 0 1 1 something in the binary format. So it becomes very difficult if you want to represent a decimal point and you don't know exactly where that decimal point is present. So it can be present after 3 means it can be present after 110.1.11, or it can be something like 1.111. Okay, so after the decimal, the number of values that are present, that is not clear to us, right? So using this particular representation, that if you have a fixed number of bits here, so in this format, if you see that the total number of bits is fixed, 32 bits, right? This is 8, this is 23, this is 1, so total is 32 bits. But let's say for that filter example that I give, so you don't know exactly how many number of bits are needed, and in that case the hardware that you need to design, it needs to have some kind of flexibility, that it needs to be able to hold 20 bits or 23 or 24 or 32 in that way, and it becomes very difficult while reconfiguring the hardware several times, because once the hardware is made it becomes difficult to reconfigure it, right? So these sort of representations make it easier for us to represent such kind of floating point numbers. And we also have floating point arithmetic units, so to take, those are specialized units to take care of such kind of needs. Okay. Does that answer your question, Suresh? Okay. Okay, so yeah, so question number 2 is also done. Okay. Okay, so question number 3, yeah, it's a factual question. So which of the following represents 0 and plus 0 and minus 0 distinctly? So it is both in sign magnitude and one's complement representations. So question A. Okay. Okay. So moving to the next question, question 4. So the decimal value of 0.5 in IEEE single precision floating point representation. Okay. So for this question, let's follow the same procedure that we did for the others. Okay. So what we need to do is convert 0.5 into binary. So 0.5 is basically 0.1 into 2 power 0. Okay, and if we convert that into standard representation of IEEE, we will have 1 into 2 power minus 1. Okay, so here the exponent is minus 1. Okay, and the mantissa, that is the part after the decimal point, it is all 0. So mantissa of all 0 and exponent of minus 1, that is option B. Okay. Okay. So now coming to question number 5. So here we need to find out the minterms of AB and AB plus ACD. So to perform this, what we need to do is we need to convert this particular equation into its canonical form. So canonical form is something which contains all the literals. Means here you can see in the first term we don't have C and D, right? And in the second term we don't have B. So first we need to ensure that this particular representation has all the terms present, whether in their complement form or their non-complement form. So let's try to do this. So to do this, let us use a property in Boolean algebra that says x plus x bar is equal to 1. Okay, so what we can do is, let's say we have AB plus ACD, so that is equals to AB into C plus C bar into D plus D bar plus ACD into B plus B bar. Okay, so we will have AB into CD plus CD bar plus C bar D plus C bar D bar plus ABCD plus AB bar CD. Okay, if you further solve it, it will be ABCD plus ABCD bar plus ABC bar D plus ABC bar D bar plus AB bar C D. Okay, so let us check out of the following options which one is correct. So ABCD is present in option B. Okay, so option B is correct. Option B has all the terms that we need. Okay, So yeah, so these problems, they may appear to be easy, but it needs some kind of working out, so that you need to have a practice with this problem. So what I will suggest is, just like the previous session that we held, I suggested you to have a pen and paper with you and solve these problems along with me. So I'll suggest you for this particular tutorial as well. Okay. So that is the answer to question number 5. Okay. Then moving on to the next question. So in question number 6, what we need to do is, we need to find out the uh, decimal equivalent of the single precision floating point number. So we know the single precision floating point. Okay. So let us try to separate it out into the fields. So we know that the first bit of the single precision floating point number, it represents the sign. So we see that it is 1. 1 means the number is going to be negative. Okay, then we pick the 8 bits, which represents the exponent. Okay, so let's try to pick out the 8 bits. This is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have the exponent as 1, 0, 0, 0, 0, 1. Okay, then let's write down the significant bit, that is 0, 1, 0, 0, 0, 0. Okay, so what does this particular value translate into? So it is 120. Okay, so this bit, it will represent 128, this particular bit. Okay, so we have 128 plus this bit, that is 1. So the biased exponent is 129. Let me write it down. Okay, we need to convert from the biased exponent to the unbiased exponent. So exactly reverse of what we did in the previous examples. Okay, so let's write it. Unbiased exponent is equal to 129 minus, here we need to subtract 127. Oh shit. Is my screen visible? Okay. Yeah, so here we will have 2. Okay. So what we can do is, we can mention this as something to the power 2, and here we have 0, 1, 0 something. Okay, we know that the IEEE format already mentions an implied 1, so let us write that 1 first. 1 dot 0, 1, 0 something. Okay, and we know that it is a negative number because the first bit is 1. Okay, so if we have 2 to the power 2, it means the decimal point should move towards the right by a position of 2, right? So let's write it as 1, 0, 1. Okay, so 101 in decimal is 5, right? So we have minus 5.0. So option C is the correct answer to this question. Okay. Does anyone have any doubt till this point? Okay, then we can proceed with the next question. So in the next question, what we need to do is, so we have a Boolean function f is equal to b bar d plus a bar d plus bd, and we need to find out the product of max terms representation. So for doing this, what we can do is, we can use Carnot maps. Okay, so let's say we have a, b, d as the variables. So let's try to draw the Carnot map. A, b, d. Okay, so here we are taking 2 variables at a time. So let's write 0, 0, 0, 1, 1, 1, 1, 0. here we have only one variable, so it is 0 1. Okay, so while drawing the Carnot maps, to avoid any mistake, what we should do is, whatever is the corresponding decimal value to that particular box, we should try to write it down. So for this thing it is 0, so this is 1, this is 2, this is 3, this is 6, this is 7, this is 4, this is 5. Okay, so here we are given a function b bar d. Okay, so when a particular literal is not present, so we will assume that both a let's say in the first case, so b bar d is written, so it means that there is a term a b bar d and also a bar b bar d that is present in this particular Boolean function, but it is not visible to us because it is reduced. Okay, so because a bar b bar d is present, so it means this is 1. Okay, similarly because a b bar d is present, so it means this is 1, right? Similarly a bar d. Okay, so a bar d will imply that a bar b bar d and a bar b d both are present. So a bar b bar d was already covered here. Okay, we just need to mention a bar b d. So a bar b d, it is this particular location. Okay, then similarly bd. So if bd is written, it means abd and a bar bd both are present. So a bar bd, it was covered in the previous term, we just need to ensure that abd is present. So this is the, okay, so now the thing is, we need to represent in product of max terms. So here whatever we have marked it as 1, so this particular thing, so it represents the min terms. Okay, and whatever is not the min term is the max term. So these columns, let us say I am marking it as 0 0 0. Okay, so these are the max terms. So what are the max terms here? 0 2 6 4. Okay, and for representing it as the product of max terms, we use this particular notation. Okay, so option B is correct. Fine. Okay, so moving on to the next question. So in this question what we have is, we need to find the sum of 12 and 1.25 using 14-bit simple floating point model. For question number 7, it is 0246. Okay, so we have a doubt. Nowadays, hardware like microcontroller and processor architecture for an application of fixed size, hence hardware will take care of these conversions and provide us the desired result. Yeah, Suresh, yeah, you are correct. But see, the thing is, those microcontrollers will also be designed by someone, right? So the one who is designing that particular microcontroller, he needs to take care of this particular floating points and those things. Okay, because those are custom made and they are made from the scratch. And so the individual who is making these things from the scratch, he needs to understand this, and we as engineers, we also need to understand this, because one day or the other we will be also designing these things. Yeah. Okay, so next we need to find out the sum of 12 and 1.25 in decimal point, and we need to find out the sum in we need to find out the sum in simple floating point model. Okay, so let me present the simple floating point model. So in the simple floating point model, the first bit is the sign bit. The next 5 bits, it is exponent, and next 8 bits, it is significant. Okay, and in the simple floating point, there is no implied one. Like we saw in the single precision floating point representation of IEEE, that we had an implied one. It means only something that is after that one is taken as the significant. But in this particular case, in the case of simple floating point, we don't have this implied one. Okay, so let us start representing both the numbers. So we have 12. So 12 will be represented in binary as 1100. Okay, so 1100 is basically like the decimal point is here. We need to move 4 places towards the left. So it means 0.11 into 2 power 4. Okay, so here the exponent is 4 and biased exponent is equal to, okay, so in this case the to find out the biased exponent, we need to add the number with 16. Okay, so just before some time someone asked a question, so why is it 16 and not 15? I guess that was the question. Let me go to that question again. Yeah, so Animesh asked, why is it 16 and not 15? So these are actually the standards that are followed. So it can be 15, means you can define your own standard and do it, but to have a uniformity across various works, we follow this particular standard. So whenever someone says that it is simple floating point, then you have to take 16 as the 16, you need to add 16 to that exponent to get the biased exponent. So here we need to do 4 plus 16, that is equals to 20, and whatever this value is present, that is our significant. So let us write it down. Okay, so before writing it down, let us convert 1.25 as well. So 1 is 1 and 25 in binary is 0.01, right? That is actually 2 to the power minus 2, so that is 0.01. So 1.25 in binary is 1.01. Okay, so here we need to move the digit to the left by 1 place, so it will be 0.101 into 2 power 1. Okay, so now you can see the exponents are different. So in this case the exponent is 4 and in this case the exponent is 1, right? So according to the rules that are defined to perform the arithmetic of simple floating point numbers, what we need to do is, whatever is the lowest exponent number, we need to increase it in a way to match the highest exponent number. So what we need to do is, we have to get 2 to the power 1 equals to 2 to the power 4. We have to multiply it with 2 to the power 3, right? So but the value of this number should not change. So to do that, what we need to do is, we need to move 3 decimal places to the left for the significant as well. Okay, so we will have 0.00101 into 2 power 4. Okay, so now the moment when the exponents are same, what we need to do is, we just need to add the significants. Okay, so now let me represent it. So it is 0, 1 0 1 0 0. Okay, so this is basically 20 being represented like this, and then we will have the 1 1 and remaining 8 bits. So remaining there will be 6 bits, so you will just append 6 zeros. Okay, so similarly you need to do for this one as well. So this one will be 0 1 0 1 0 0, and this is 0 0 0 1 0 1. Okay, and you just need to add the significance to obtain the result. Sign bit will be same, the exponent will also be same. Sorry, the exponent is 1 0 1 0 0. Okay, only the significance will be added. So now let's add the significance. It is 1 1 6 zeros plus 0 0 1 0 1. Yeah, 0 0 1 0 1 0 1 1. Okay, so the final result will be this one, 0 1 0 1 0 0. Okay, so this is the final result. Okay, sure, I'll repeat this one again. So option C is the correct answer. So yeah, so Utpal, so someone asked me to repeat it. Okay, Upendra. Yeah, sure, I'll repeat this one. So first what I did is I converted 12 in the binary, then I represented it in the standard notation for doing the simple floating point arithmetic. That means you need to have a 0 point some value into 2 to the power exponent. Then I converted the exponent to biased exponent. So in simple floating point arithmetic, to convert into biased exponent, what you need to do is whatever exponent is present, you add 16 to it. So after adding 16 to 4, I got 20. Then I wrote the significand of this particular value, that was after the decimal point, whatever is the value, that is the significand. So I wrote 1 1 and just appended zeros to make it 8 bits. Then for the 1.251, I did the same thing. I converted 1.25 into binary first, so that is 1.01. But I need, after representing it in the standard notation for the simple floating point, it becomes 0.101 into 2 power 1. But now you can see we have two different exponents, that is 2 power 4 and 2 power 1. And according to the rule, what we need to do is whichever has the lowest exponent, which is 2 power 1 in this case, so we need to multiply it with 2 power x such that it is equal to the highest exponent, that is 2 power 4. So we need to multiply 2 power 1 with 2 power 3. Okay, but if we multiply it directly with 2 power 3, what is going to happen is the complete value of this number changes. So to maintain neutrality, what I do is I also multiply it with 2 power minus 3. Okay, so I multiply 2 power minus 3 to the significand, and I multiply 2 power 3 to the exponent. It doesn't change the value of this number. So because of multiplication with 2 power minus 3, what happens? The decimal point moves to the left by 3 places. Okay, and after this moves to the left by 3 places, this is what the significand is. So I have the two representations, the exponents are equal. What I need to do is simply add the significants. So this is what I did here. What if there is an overflow? So overflow is not covered in this particular section. is the answer clear, Upendra? The explanation. Okay. Okay, so moving on to the next question. So the next question is about, okay, a function of Boolean variables x, y, z is expressed in terms of minterm as how 0.25 convert to 0.01. Okay, so 0.01, I converted it on in my mind, but so 0.01, it means it is 2 to the power minus 2, right? So 2 to the power minus 2 is 1 by 4, and 1 by 4 is 0.25. Is that clear? Yeah, so you can remember that 0.1 is actually 0.5, 0.01 is 0.25, and similarly, like 0.001 will be 0.125. Okay, so just to make your calculations faster. Okay, so in question 9 we have a expression that says you take 1, 2, 5, 6, 7 summation of that, and we need to find out which one is the product of sums representation of that function. Okay, so for this question, what we can do is we can construct a Carnot map again. What is the answer of question number 8? Option C. Okay. Yeah. So let me write x, y, and one variable here. Construct the Carnot maps 0, 0. Okay, then we are said that f is equal to summation of 1 to 5, 6, 7. So let us mark 1 at those location, 1, 2, 5, 6, 7. Did we miss any value? 1, 2, 5, 6, 7. Okay, so now what we need to do is we need to find out the product of sums. So product of sums will be 0, 3, 4. Okay, so 0, 3, 4, it needs to be represented in product of sums format. So while representing it in product of sums format, what we need to do is whatever is the value that is present. So let us say at the 0th location. So for 0th location, the value would have been x bar, y bar, z bar. For 3rd location, the value would have been x bar, y, z. For the 4th location, the value would have been x, y bar, z bar. So here what we need to do is, for representing in product of sums, you write x bar, y bar, z bar as x plus y plus z. Similarly, for x bar, y, z, you represent it as x plus y bar plus z bar. So please observe what I am doing here. What I do is, like, to convert from the product form to the summation form, what I am doing is I am complementing the variables and putting it in a sum format. Okay. Similarly, for 4, x, y bar, z bar, we will have x bar, y plus z. Okay, so our final product of sum representation will be x plus y plus z into x plus y bar plus z bar into x bar plus y plus z. Okay, that is option number B. Okay. Okay, so moving on to the next question. So what we need to do is we need to find out the simplified form of this function, that is represented as summation of 1, 5, 6, 7, 11, 12, 13, 15. So we need to construct a 4 variable Carnot map. Okay, let me use the new page. So I'll write AB here, CD here, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay, we have 0, 1, 3, 2, 4, 5, 7, 6. This is 14, 15, 13, 12, 8, 9, 11, 10. Okay, 9, 11, 10. And what were the value? 1, 5, 6, 7, 11, 12, 13, 15. So 1, 5, 6, 7, 13, 11, 15. Okay, so here what we need to do is to reduce the number of terms. What we can do is we can group the adjacent. So if we have adjacent numbers in 2 to the power 1, then we can group those numbers. Okay, so let's say we group this one. These two are adjacent, we can group them. These two are adjacent, we can group them. These two are adjacent, we can group them. These two are also adjacent, we can group them. We can also have a group that is something like this, that takes care of 4 numbers that are 4 ones that are present at the center, but actually those ones are already covered by the other 4 circles, right? So adding that extra innermost circle will be redundant, correct? So okay, so let us try to write the minimized form. Here we will have A bar B C plus, then we will have A bar C bar D plus A C D plus A B C bar. Okay, so this is our reduced form that we were supposed to bring. A bar B C, A bar C bar D, A B C bar. Okay, so this is option C. So option C is the correct one. Okay, does anyone have any doubt in this question? Okay. And the session recording as well as the slides, why not group of 4? Yeah, sure, we can take group of 4 as well. As I explained, this particular inner circle, if you can see 5, 13, 7 and 15, it forms a group of 4. But this will be of no additional use to us because those ones are already covered by the other 4 circles. Like this one, this one, this one, this one. It covers 5, 7, 13 and 15. So it will just add an extra term, but it won't give any additional information. Okay, I hope that clears the doubt. Okay, so the next question is, so we have a small problem on Boolean algebra, and we need to minimize this particular equation. Okay, so let us write this equation: AB plus ABC plus AB into D plus E. Okay. So what we can do is, let us start by combining okay. Okay, so 1 plus any variable, it is going to be 1. Okay. So here we will have AB plus AB. So let me write it down. 1 plus X is equal to 1. AB into D plus E. So again we will take AB common. So it will be 1 plus D plus E. Okay. Again this is of the format 1 plus X. So it will be 1 and we will be only left with AB. Yes, we can take directly AB common from all the terms, but I did it in a step-by-step format so that everyone is able to follow it. Okay, so the answer is option A. Okay, then what we need to do is, we are given a Boolean expression and we need to simplify it. So for simplifying, okay, so whenever you see such a thing, like you have the variables present and you have a bar over it, so the first thing that should strike your mind is the De Morgan's theorem. Okay, so we are going to use the same thing here. So what we will do is, let me write down this thing first. Okay, so if we have something like A plus B whole bar, so it will be A bar dot B bar. Okay, so it will be A plus B bar plus C plus D bar whole bar dot B plus C bar whole bar. That will simplify as A plus B bar whole bar dot C plus D bar whole bar dot B bar dot C. That will again simplify as A bar plus B plus, this will be C bar plus D plus dot B bar dot C. So here you can see that we have the variable in both complement as well as non-complement form. Okay, so whenever we have x dot x bar, the equation reduces to 0. So the final answer is 0. Okay. So D is the correct option. Okay, so moving on to the next question. So in the next question we are given a truth table. Okay, and we need to find the product of some form for this particular question. Okay, so for finding the product of sum, again the same thing, that you need to consider the places where the function is 0. Okay, so for these particular value the function is 0. Okay, so we can write it as in the product of sum format, just like we did before 2 examples. Okay, so this is A bar, so A bar will be A plus B bar becomes B plus C, so C will become C bar into A. Okay, A will become A bar plus B bar plus C bar and product of both of them. Okay, so the right answer is option B. Okay, okay, so let us move on to the next question. So the next question is again related to IEEE 754 single precision format. So this is the floating point representation and we need to find the decimal form of this particular number. Okay, so the first thing that we see is the sign bit. So the sign bit is 1, it means the number is negative. Okay, The next thing that we see is the exponent. So this one translates to okay, so this bit represents 128, this bit represents 2, this bit represents 1. So this value is 128 plus 2 plus 1. This is 3, 128 plus 3 equal to 131. Okay, so this is the biased exponent. To get from biased to unbiased in the IEEE single precision format, what we need to do is we need to subtract that particular number with 127. So we will have 131 minus 127, that is 4. Okay, so this becomes 2 to the power 4. Then we have, okay, so we will have an implied 1 because IEEE standard represents in that way. So 1.101, rest all zeros, the rest zeros doesn't make any sense. So this is the value and we need to represent it in decimal format. So it is minus, then shift to the right by 1, 2, 3, 4. So we'll have 1, 1, 1, 0, 1, 0. Okay, so it will be this is for 2. So we have 2 plus, this is 8 plus 16. This is 2 plus 8 or 10, 10 minus 26. Okay, minus 26 base 10. So the correct answer is option C. Sorry Suresh, I could not get your doubt. So what is it about relation between exponent and significant for any bit floating point representation? Suresh, can you explain your doubt a bit? How many bits? Okay, so exponent in this particular case will be 8 bits because it is single precision format, and the significant will be 23 bits. Does that answer your question? Okay, so okay Upendra, so I'll explain all the problems again after the last problem, and you can let me know which one you are facing issues with. Okay, so moving on to the final problem that we have, that is, okay, so we have to find out which of the following gives the simplified sum of product expression for this particular Boolean expression. Okay, A, B, C, and A is the MSB and C is the LSB. So MSB, LSB means, like, let's say you have a number 101011. So MSB will represent this one. This is the most significant bit, and LSB represents this one, that is the least significant bit. Okay, so now let us construct the Carnot map. A, B, C 0 0 0 1 1 1 1 0 0 1. Okay. 0 2 6 4 1 3 7 5. So it says M0 M2 M3 M5. So M0 M2 M3 M5. So this can be grouped into 1, this can be grouped into 1, and this will stay alone. So this will be A bar, sorry, this is A, B bar, C. Okay, and this one is grouped into 1, it becomes A bar, B, and this one is grouped into 1, this becomes C bar, A bar. Okay, so the final result that we have is A, B bar, C plus A bar, C bar plus A bar, B. Okay, that is option number B. Okay. Is that clear? So till now, whatever problems we have solved, does anyone have any doubt? Yeah, Debadrita. So you can question number 14. Okay. Yeah. So in question number 14, okay. Yeah, so in question number 14, where exactly do you have the doubt? Should I explain it again? Okay. Yeah. So question number 14, what I did is first, like whatever value is mentioned, so the first step that you need to perform is you, based on the number of bits, you try to separate out the fields. Okay. So first you separate out the sign field, then you separate out the exponent field, then you separate out the significant field. Okay. So that's what I did. So first I took out the sign field. So the sign field was 1. So that represents that my number is negative. Okay. Then the next thing that I did is I took the exponent field. Okay. So exponent field, I know that the width of that exponent field is 8 bits. So I just chose the next 8 bits after the sign bit. Okay. Then coming to the significant field. So the significant field is 1, 0, 1, this thing. Okay, till the end. Okay, so then what I try to do is I try to convert the exponent field into the exponent field that is mentioned here is actually the biased exponent field, right? So I need to convert the biased exponent field into unbiased exponent field. So what I did is I converted the biased exponent field in a decimal format so that it will be easier for me to calculate. Okay, so as you can see, so we have a 1 at the very beginning. So 1 at the very beginning, it represents that it is 128. Okay, then we have a 1 at the end. So 1 at the end means the value is 1. Then you have the 1 at the second position, that means the value is 2. So I just converted this whatever value was given in the exponent field into decimal. Okay, that is 131. Okay, then for converting this particular biased exponent into unbiased exponent, what I did is I subtracted 127. Okay, because from normal form to that floating point single precision representation, to get to that form, what we used to do is we used to add a bias of 127, right? So in this case, what we will do is we need to get back to the normal form, so we have to subtract 127. So that's what I did, and I got 4. Okay, so it means my exponent portion is 2 to the power 4. Then based on the IEEE standard, like whatever is the rule, so the rule says that there has to be an implied 1. Okay, so before presenting the significant, what I did is before the decimal point I presented a 1. Okay, and after that whatever is the significant field, it will be copied as it is. Okay, then what I did is I need to multiply into 2 power 4. So multiplication with 2 to the power n, it means shifting of decimal point towards the right by n positions. So same thing I did here, I moved towards the right by n positions, that is by 4 positions. Okay, so what I will obtain is 11010, right? And this number I convert it into decimal. So when I convert into decimal, this is the value, minus 26. does that answer your question, Upendra and Debadrita? Yeah. So whenever you have 2 to the power x where x is positive, it means you are performing multiplication, and multiplication means uh, like you shift the decimal place towards the right? But if you have something like 2 to the power minus x, where x is a positive number, okay, so it means it is basically you are dividing it, and it means you have to move the decimal place towards the left. Okay. So yeah, so coming to Upendra's question, okay, so can you please elaborate um, where is the problem exactly while solving these form of questions? Is it the floating point representation itself? Okay. Yeah, so for that, what you can do is in the lecture slides, so it has been mentioned that for single precision floating point, this is the particular representation. So you just need to remember how many bits are being used. Okay. So basically the representations, they differ only in the bias value and the number of bits that are being used. Okay. So like single precision will have 8 bits exponent or something, and the double precision one will have 11 bits. So just make sure that you have the appropriate mapping, that you know single precision will have 8 bits and all, and accordingly the remaining steps, they remain the same, right? And yeah, for the IEEE standard single precision floating point, there is an exception that the implied one comes into the picture. Okay, and in the simple one there is no implied one. Correct. So if you remember these 3 points, then I think you should not face any difficulty. But if you still face any difficulty, what you can do is, like, this particular recorded session will be available to you. So I hope the NPTEL team has shared a link where the sessions are being updated. So you can go through that session, and you can try solving it again on your own. And if you still, yeah, Vikas. Yeah, you can type your question here. So yeah, if you still face any difficulty, you can post your doubts on the forum, and if it is related to this, can you unmute? No, Vikas, I can't unmute. So you can post your queries in this chat box itself, or you can, if like while solving these questions again, if you have a doubt, you can post it on the course forum. Okay, let me summarize what we did today. Okay, Vikas. No, the solutions to the week 2 assignments can't be discussed here. So that is not allowed, Vikas. Okay. Anyways, let us just summarize what we did today. So first we started with the floating point number. So the representation, how we represent that particular number. Okay. Then we saw two basic representations that are mentioned by IEEE, that is the single precision floating point and the double precision floating point representation. We saw the different fields that are involved here: the sign, the exponent, and the significant. And how many bits are needed for the exponent field and the significant field, which are mentioned by the IEEE standards. Okay, then we started solving the problems. Okay, starting with a very straightforward question on representing the number 23 in the single precision floating point binary representation. Okay, then we started solving it. Like, first you convert 23 into the binary representation. From binary representation you move to the standard representation, which says where you place the decimal point exactly. Like in the simple representation, we will place the decimal point before any number starts, right? But in the IEEE fixed point single precision decimal binary representation, we will place the decimal point just after the first one, and that first one is not represented in that significant field because that one is already implied. It means whatever is present in the significant field, it will imply that it is present after the decimal point after the first one. So this is called as implied one, right? And then what we do is, whatever is the exponent that is present here, we need to convert that exponent into biased exponent. And in the IEEE single precision format, we need to add plus 127 to get the biased exponent form. So this biased exponent takes this particular field, okay, and the significant is taken by anything that is present after the decimal point. Okay, so that was our question 1. In question 2, so there was just a bit of difference, that 0.75 was given, which is having a fractional part. In the previous question, that was 23, there was no fractional part. So here we have the fractional part, but the procedure is again same. So what we do is we get the binary value of 0.75, and that thing we convert into the standard notation, that we will have the implied one, and after that all the remaining digits into 2 to the power whatever is the exponent. So here you can see we have 2 to the power minus 1. So to find the biased exponent, we add minus 1 to 127, it becomes 126. 126 is represented in terms of binary here. So this is the biased exponent, and this then goes to the field directly. Then we find the significant. So the significant is just in the standard notation, whatever is present after the decimal point, it finds its place in the significant. Okay. Okay, so that's how we obtain here, and it has a minus sign. So minus sign means the sign bit will be 1. Okay, so this is question 3. It is just a factual question. It says like which of the following representations have plus 0 and minus 0 distinctly. So it is only in sign magnitude and 1's complement representation. Okay. Then question 4 was also straightforward. You just need to convert 0.5 into the single precision floating point representation that we did in the previous 2 questions. There you find what is the exponent. We see that it is minus 1. Then you find what is the mantissa. Mantissa is anything after that decimal point, that is 0 in this case. So the option B was the suitable option. Okay. Yeah. So then question number 5. So question number 5 was related to Boolean algebra. So here we just needed to find out what are the minterms of AB plus ACD, and what we try to do is we try to put it in a canonical form. So for putting it in canonical form, what we do, whatever variable is missing, we just try to multiply it using this property, x plus x bar is equal to 1. Okay, so in the first case C and D were missing, so I just added C plus C bar into D plus D bar. and in the second case b plus b bar was missing, and I just added that into the second term. The next thing what I did is I just multiplied and I just tried to solve it. So after solving, this is the answer that we obtained. Yeah. So the next thing is we had to find out the decimal equivalent of the single precision floating point number. The floating point number was mentioned here, and to solve these questions what I mentioned is, so whenever you have a number like this, start from the left side, okay, pick whatever is the first point, first bit. So the first bit will represent your sign. So the sign bit is 1, so it means the number is negative, okay. The next 8 bits will represent your exponent. So basically this is the biased exponent. So the biased exponent in this particular question was 129. Okay, from biased exponent you need to come to the unbiased exponent form. So the unbiased exponent is obtained after subtracting 127. You have 129 minus 127, that is 2. Then the rest of the bits, they actually represent the significant, right? So you just write the significant directly here, but before that decimal point you mentioned the implied 1, okay, because in the IEEE specified rules it says that you need to have an implied 1. So the number was represented as minus 1.010 into 2 power 2. So because it was multiplied with 2 power 2, we need to move 2 places to the right of decimal, okay. Then it comes, okay, then we have the product of max terms. So we have the Boolean expression given, we draw the Carnot maps, okay, and we just mark the bits in the min term, and whatever is left, that is the max term, okay. And yeah, as I mentioned, so while solving while using the Carnot maps, make sure that you have marked the indexes like this. So whatever that position represents, the value that the position holds, you should have a practice of marking that value, because in bigger and bigger equation it becomes a bit complicated to track it, like which particular box represents which value. Okay, so just make a small 1, 2 or such number and try to resolve it. So here also we did the same thing, and we observed that 0, 2, 4, 6 are the max terms. Okay, so similarly for question number 8, we had to find the sum of these two numbers. So the first thing that we did is we converted 12 and 1.25 into the simple floating point representation. Whatever is given in the rules, based on that we convert them into simple floating point representation. Then we saw that the exponents for the first number and the exponent for the second number, they were different. So to resolve that one, what we need to do is we found out which exponent was the lowest. We saw that the second number's exponent was the lowest, and then what we did is we multiplied the second number with another number such that the exponents become equal. So another number that was needed was 2 power 3, but as we are multiplying the exponent with 2 power 3, we also need to multiply into 2 power minus 3 so as to keep the value same, okay. So after multiplication with 2 power 3, 2 power 1 becomes 2 power 4, and 2 power minus 3 goes to the significant, and it leads to movement of the decimal place to the left, okay. So it will move to the left by 3 places because we are multiplying 2 power minus 3. And once we have the final representations, simple floating point model, in floating point model, we can directly add the significance over here, okay, and this is our final result. Then the next question focused on, so we needed to find out the product of some representation. So what we did is whatever expression was given to us, we tried to solve the Carnot maps. From the Carnot maps, okay, we did not do any reduction here, so I just drew it for the representation sake to see which all terms are 0. I figured those terms out and I presented it here. Okay, and for product of sum representation, I just showed like how we need to map the multiplication once with the addition. Okay, the complements become non-complements and non-complements are complemented, and then you just take the product of them. Okay, so the next question was related to simplification of this entire thing. So for that we used Carnot map, and in Carnot map what we did is we tried to pair the adjacent ones. Okay, and after pairing the adjacent ones, we see that the final term, the simplified one, is this value. Okay, then for the next question, question number 11, we had to reduce this particular Boolean expression that was given to us, and I used the 1 plus x is equal to 1 property of Boolean algebra to reduce the expression. As someone rightly mentioned that yeah, we can take AB common from the very beginning. So if you take AB common from the very beginning, this particular term will be 1. 1 plus something is always 1. So AB into 1 is equal to AB, right? I did it in a step-by-step fashion so that the steps are clear for everyone. Okay, so the next question was related to again Boolean algebra, and we had to simplify it. So I did the simplification using the De Morgan's law, and from this I went to this using this property of De Morgan's. Then at the end we arrive at this simplified form, and we can see the complements present here, B bar B and C bar C. So if both complement and non-complement are in product form, then the result becomes 0, and anything multiplied by 0 is 0. Okay, so question number 13 was related to expression in product of sum format. So we just pick out those values where f is equal to 0. Okay, and then again we represent it in POS format as we discussed earlier before the two questions. Okay, so the next one was question 14. We had to convert this floating point representation into the decimal format. So what we did is we just tried to figure out which was the sign field, which one was the exponent field, and which one was the significant field. After figuring it out, what we try to do is we convert the exponent into decimal format just for our ease of calculation. And after you convert into decimal format, you convert this particular biased exponent field to unbiased one by subtracting by subtracting 127. Then you obtain 4. Then the remaining set of bits that are present apart from the sign and exponent, that is the significant. So that significant is represented here. Okay, and the 1 is already implied, so we just write the 1 here. Okay, and we try to convert it again back to decimal by the normal binary to decimal conversion process that we have seen throughout week 1 as well as in week 2 some portions as well. And the last was related to getting the simplified sum of products expression that has been done using Carnot maps. Okay, and so here I also mentioned what is MSB and what is LSB. Okay, so these are actually the foundations of digital electronics, digital circuits, and so you need to practice them several times so as to get a hold of it. Okay, so there is a question: how can we identify whether we have to bias the exponent or unbias the exponent? Okay, so if it is already represented in the floating point format, it means that the exponent that is present here is biased, right? So if you want to convert from floating point format to a scientific notation or any other standard format, so what you need to do is you need to unbias that exponent. Okay, does that answer your question, Devadrita? Okay. Okay, so these slides and the recorded lecture, it will be shared by the NPTEL team. So the recorded lecture will be available on my YouTube channel, NPTEL TA Arpit Bal, PMRF, and the slides will be shared by the the NPTEL team. Yeah, so you can go through the slides again and you can practice these questions without looking at the options or the solutions. Okay, and then try to check the solution, so that will be more beneficial. So whatever we have covered in today's lecture, so is there any the video available? Yeah, the video is available. You can check the YouTube channel, NPTEL TA Arpit Bal. So if you click that, week 1 session is uploaded already on the same day. Week 2 session I'll upload it in an hour. Okay, this is being recorded. Yeah. So is there any doubt related to today's session? So whatever topics we covered related to the floating point representation, floating point arithmetic, basics of Boolean algebra. So these were the three main topics that were covered today. Is there any doubt related to that? Of whatever problems we solved? Okay. Okay, so if you still have any doubt, yeah, you can ask your queries in the NPTEL questions section. So NPTEL website, it has a section for asking the queries, and that will direct you to a forum. In that forum you can post your queries, whatever you have. You can mention this particular session, that the Saturday 3 to 5 session that was taken by me, something. Sorry, Sanket, I didn't get your question. Are all the sessions same? Okay, are all the sessions conducted by different TAs? It depends. So I cannot comment on that. Maybe you can attend and check. If they are similar, then maybe you can attend the most preferred one that is feasible for you. Vikas has a question. Zero question 04. Ask for a second. Same answer is 28. Question 15 has two, same answer is 28. Which two? But why did you convert them into? I mean, question 15 doesn't have any 28. See, Vikas, you can't ask assignment questions, so that is prohibited. Industrial applications of all these things. So I already mentioned it. So I guess who asked that question? Yeah. So I actually already answered it in the beginning of this thing, but anyways, so industrial application is mostly related to. I gave an example of a filter. Then you can have other specific calculations, like anywhere where, let's say, multiplication of a value is involved. Okay, so you are not going to multiply integers with integer always. So one value can be a floating point number. Let's say you are making a hardware for solving some sort of differential equation or something, and the coefficients that are present are not integers. Okay, and so those floating point numbers, they need to have a specific hardware for them, because you see, after the decimal point you don't know how many bits will be needed, right? So if you don't know how many bits will be needed, so you need to make a very flexible hardware which needs to accommodate multiple bit operation, right? So it needs to be working for 8-bit operation, 16-bit after the decimal operation, so on and so forth. So by using these notations, by using these representations, what we can do is we can make a hardware which does not need that degree of reconfigurability. Okay, and yeah, so this particular things, they find application in all sorts of industry related to signal processing, even machine learning hardwares, so where you have certain weights that you need to multiply, then hardware accelerators, and other digital signal processors. Yeah, I hope that answers your question, Omkar. Yeah, okay. So Sanket, yeah, whatever questions that I have solved today, so the slides will be shared with you afterwards by the NPTEL team. Okay, and you can also go through that, go through the recorded session of this particular video. Is there any other question that you guys have? Okay, and yeah, and I'll strongly recommend everyone to go through those lectures before uh, joining the live session, so it will help them to understand the live sessions better, and so to take benefits from this live session, it will make their practice better, and conceptual clarity will be better once if you go through that lectures and then practice these problems. And after this session, I'll suggest you again go through the problems without seeing the solution or the steps or even the options, and try to solve them on your own. And if we study only assignment, then it is okay. See, I can't comment on that. I'm not preparing the questions for the exams or something. But yeah, the concepts that we cover in these sessions, they will be helpful for your, not only for your assignments or your exams, they will also be helpful for, like, in your future subjects that you are planning to take. So I can't comment whether those assignment questions will be helpful for your exams. Means they will be helpful in a way that conceptually they will be covering most of the topics, but it's not like the same questions will be appearing or something. I can't comment on that. Is there any other doubt? If not, then we can end today's session. So I'll be here around for 5 more minutes. So if anyone has any queries, then they can ask me here itself. If not, they can also go through that recorded lecture that will be available on YouTube after an hour or something. The NPTEL team will share both the link to the YouTube channel as well as the slides, the annotated slides. Okay. Thank you everyone.